So today we are going to talk about pumps and pump curves, pump energy efficiency, when people are wasting money, running their pumps too much, and a lot of us don't know about it. Well, Christian is going to explain it. Hey, Chris, can you advance the slide? So Christian, he still works for us at Abraxas as a senior engineer. He is maybe the most knowledgeable person I know in our business about all the different equipment, how it works, all the different measuring equipment, how to use it. He seems to know just about everything. I'm sorry, nobody does in our business, but he comes really close. He was raised in the trades, or at least that's how he came up. So he's started as a hands-on guy rather than, a lot of us who are engineers and we were just Excel and math people who didn't really understand equipment. He was an equipment guy. So he has that different type of knowledge. Right now he works for CBRE. And I'm going to let Chris explain more of his past and give his resume, and he's going to just move on from there. Thanks for coming, guys.
Thank you, John. Hope everybody can hear me just fine. So I started about 20 years in mechanical service, started with a mechanical contractor, transitioned into building automation during that time, became the rep for that mechanical contractor, and then transitioned to a controls vendor, actually JCI. All along that whole time, I was a TAB, what they call a certified professional. That's really where I got into the pumps side, where I was testing and making sure they were working right. But we also focused a lot on energy management, because that, just testing it to make sure it works does not equal energy management. All that it means is it's working. So we started looking at this equipment on how to work more efficiently. Did a lot of commissioning, always focused on the energy on that side also. Where could we make improvements? Anything that we could do to reduce energy everywhere we could. But now we're doing that for a hospital system here based in Texas and across Louisiana and in New Mexico. It's nothing but hospitals that I work on right now, and my goal is to reduce energy everywhere I can. And I'll give you some real-world examples of systems I've been working on. These are actual systems that we're actually doing something about, and it's all focused on pumps. So that's kind of the quick resume. So we're ready to get going. All right. So I'm sure that if you have or haven't, you've seen what this is. This is a pump curve. Why we care about that, this is really one of the biggest questions, and I actually had somebody say that they don't think they've ever looked at a pump curve when they were doing a project for energy management. And so the goal of this presentation is to maybe give you a little more insight into something that you may or may not be using, to give you a little bit better feel for where you can make improvements. So a pump curve is a graphic representation of the performance characteristics of a pump under varying conditions, okay? So each one of these curves represents an impeller. We'll go through the parts of it piece by piece. This is a typical pump curve. The critical parts are the vertical lines, the lines going straight up represent the head produced by the pump against the flow, which is going across the bottom. The bottom left-hand corner is 0 for both of those lines. The curve, the dark thick line, represents the actual performance of the pump across those values. So the head increases from the bottom up, the flow increases from the left to the right. All right, so that's a simple pump curve. For those of you who may not know what the parts of a pump are, let's talk a little bit about pumps and fundamentals. So we talk about pumps as inlet and outlet, of course. Typically we talk about water. Water is probably the most common thing that we pump. A foot, when we talk about the pressures, a foot of water equals 0.433 psi. So when we talk about pump curves, it's going to measure the head in feet of water. That's pressure. Conversely, 1 psi of water equals about 2.37 feet. So in other words, a pound of pressure can push water 2.37 feet. Atmospheric pressure, of course, is 14.7 psi absolute, or 33.96 feet. That's the maximum vertical feet the inlet of a pump can lift at atmosphere. Basically, the atmosphere is pushing the water into the pump if you have an open system, like a cooling tower or something like that. In fact, that question came up today before this presentation on a phone call that I had to point out that one of the engineers had made a mistake on a cooling tower and needed a pump that needed a lot less suction pressure to get the water into the pump than the one that they had selected, and they were pulling vortices or actual whirlpools in the cooling tower and pulling in air. But they had to realize that. Now on this graphic, I've highlighted the critical parts: the inlet, the outlet, the casing of the pump, which could be a standard casing, but the impeller is the part that rotates inside the casing, and that's the part that makes the curves. So when we look at a pump curve, you're seeing different impellers on this same curve. Commercial pumps have performance curves showing the following data for a given pump speed. Now remember, the pump curves are made at full speed. Now that full speed could be 3,600 RPM, 1,800 RPM. You have to look at the curve you're looking at to see which speed we're talking about. That's critical. So you need to make sure that you've got the right pump speed first off for the pump you're looking at. Total head versus flow in GPM. Again, the flow is across the bottom, the head is in the vertical. Total head versus flow for various impeller diameters. Again, we've got 1, 2, 3, 4, 5, 6 impellers on this curve. Pump efficiency at various operating points. This is going to be critical as we talk about selection and how we're operating. The efficiency is where a lot of questions get answered. Brake horsepower, that's our part in energy management, what we actually have to have in order to move the water. And if we can make any reductions or if it's practical. The net positive suction head, that's what I was talking about at a cooling tower. They did not have enough pressure pushing the water into the pump to get the water moving through the pump at the right flow rate. If you don't do that, and you're in a closed system, basically where you're not able to pull air in, you will actually cause a vacuum in the suction of the pump and boil the water. You reduce the atmospheric pressure to the point that the water will boil inside the pump. Now, I've actually had this happen more than once, and I'm ashamed to say that, because a lot of people will have problems with pumping, and the first thing I look for is, do we have the right amount of water coming into the pump? In a closed system, in other words, pump the water around the pipes through the coils, chiller, and back to the pump. You push out a gallon of water, it comes back a gallon the other side, unless you have a restriction somewhere that chokes off the water getting back. And if that restriction works through the entire system, it will starve or negate the effect of the pump. Right? So that's something to watch for. But you'll see where you're at on this pump curve. That's something that you don't get when you just walk up to the pump.
Chris, I have a couple questions.
Sure.
Sorry. So you mentioned, can you go back one slide? Yeah. So you said for different speed, or I wanted to make sure I understood this. For different speeds, does that mean you're going to get different curves or different sheets of paper? Is that what you mean?
Yes, sir. That's what I mean. Got to look at usually it's at the top of the curve. That's on the sheet. It'll tell you what speed that these curves are generated at.
Good.
And again, they're at maximum speed. Okay, so we'll talk a little bit about variable speed later in the presentation. But
Excellent.
These curves are made at full speed.
Okay, and then 2 slides back, sorry. You mentioned a 33, one slide back, one more back. You mentioned a 33.96 feet. So atmospheric pressure will push water 33.96. Does that assume that the other side has a vacuum? Is that the idea, that we have atmospheric pressure on one side and a vacuum on the other?
No, it's the maximum distance. Like if you were pulling out of a pit, okay, you had the suction of your pump down in a pit, a hose or something. If you notice, if you've ever had to pump out a hole that's filled up with water, the hose on that pump is only 30 something feet, because you will not be able to pull the water any further than that. If you had to do that, like if you had a hole that's deeper than that, you had to stage up. You would have to put one at the bottom, and then another one 30 more feet up, and then another one 30 more feet up in order to get the water from one to the next. But you cannot pull the water any further than 33.96 feet
I
at
didn't know that.
atmosphere.
That's good. Thank you.
Okay. So if your suction, this is what the reason I brought it up. If your suction pressure does that, if you have a gauge on the suction side of the pump and it's looking negative, and they will actually do this, then that's what you're actually doing. You're pulling a vacuum on the suction side of the pump. So keeping going. All right. So the curve, it's based on the impeller diameter, different diameters in the same case. You can put a different size. At operating at full speed, each curve represents a different impeller. So if you notice, this would be the biggest one we can put in this pump. It's 15 inches. Okay, then the next one down is 14. That's the next curve. Okay, the next one down is 13, 12, and 11. And the final is the one that's 10 at the very bottom. Okay, but that means that this pump can use all of these impellers. You just have one installed per pump though, but you got to be able to remember which one you're dealing with, because they sometimes will stamp them on the nameplate, not always, but this same casing can handle this family, these 6 impellers. So you can have whatever you want put in here. Now this curve also includes limit lines, okay? Not all of them do, but those red lines represent where they do not recommend you operate outside of these parameters. Those dotted lines on the curves are telling you that this probably is not the best operation for the pump for whatever reason. And it includes both at very low flow, below 200 GPM, if you look at the bottom, on the left-hand side, and above what we call wide open flow, which is if you had it pumping just into space. You didn't have anything resisting flow on the right-hand side. So this pump could theoretically pump 1400 GPM with the largest impeller at the very extreme end. But above that, they don't recommend you operate in that range. Okay, so not all the curves have this, but this one happens to include it. And we'll talk a little bit more about that later. So the vertical line represents the total head in feet. It increases from 0 at the bottom all the way up. And in this case, we're just below 100 feet at the 15-inch diameter curve. It's measured in feet of water. You can get these also in metric. This is the system's resistance to flow, determined by the design of the system, including resistance due to the pipe size and length, the fittings, the equipment that requires design flow, like chillers, boilers, coils. It's measured across the pump section and discharge right at the pump. So this is not your pressure differential out on the system. So if you're looking at a control system that measures differential pressure, that's usually 2/3 of the way down the system. That's going to come up in a discussion later on, but this is not what we're talking about. This is right at the pump. So this is the pump's ability to overcome this resistance at different flow rates on the curve. Okay? The ability to pump a quantity of water against this resistance. Remember this. Now, if you notice, and we'll talk again, we'll bring this up multiple times. We start talking about flow. The flow is across the bottom. So this is the capacity that these pumps, these curves will produce, but where they intersect on the curve, if you draw straight up, let's say in this case 1,000 GPM, where it intersects each one of these curves and you move to the right, or the left, sorry, you'll notice where it intersects the line for the pump head. So what it says is, we take example our 15-inch diameter curve. At 1,000 GPM, it will move 1,000 GPM somewhere in the 75 feet range, okay? So if you had resistance above 75 feet, your flow is going to go down. It moves the line to the left if your resistance is higher than 75 feet. And conversely, if it's below 75 feet, it moves the line to the right. You can actually pump more. So the higher the resistance to flow, the lower your flow. The less resistance to flow, the higher the flow. So the less the head, the higher the flow. The higher the flow, I mean, the higher the head, the less the flow. That pump can only pump against a certain resistance. If you notice, on our first line there for the 15-inch diameter, it falls right in line with the best efficiency also. We'll talk about that in a moment. But you want to select the impeller size to deliver the design GPM against your system resistance. So if you design the system against a certain resistance, then you're going to go select a pump that will pump the right amount of flow against that resistance. Okay, efficiencies. Pump efficiency is going to change according to what impeller you got. Now, I've outlined in this case the green lines. Okay, the red lines are where the efficiency is starting to fall off. So the best efficiency this pump can exhibit is in the 81% range, and that's only including in this case, two impeller curves. If you can accept 80% efficiency, you get down into a third curve. However, if you start dropping off at 75, you can get into a fourth curve, but it's way down the line. And if that's acceptable, fine. But this is basically the pump's impeller ability to move that water. Pumps are non-positive displacement, in these cases centrifugal. So if you're going to lose, in other words, every turn of the impeller doesn't move 100% of the water. It moves, in this case, 81% is the best we can expect out of this pump. And it falls off from there, of course, according to which size you use and how much your flow. Again, the resistance is going to matter. It moves the efficiency curve to the left. And the amount of flow, eventually get to the point that you can't move the water efficiently, it moves to the right. So that's why these curves show up on both sides of the curve towards the higher head and the higher flow. Horsepower. This is where energy management comes into play. So I've outlined each one of the horsepowers, and if you select a pump, again, the limits are coming into play. They do not recommend that you use this pump outside these lines. Those dotted sections of the curves are in the bad zone. So if I pull up the first one, everything below that line to the left, curves will work on that 20 horsepower line. Okay, the next line down is a 15 horsepower, and these are the standard motor sizes. The next line down goes to 10 horsepower, and then the next down to 7.5. So you want to select, if you chose your flow and resistance, you have to select a motor larger than where you land on your pump curve in order to move that water. Otherwise, you will have a problem. You will not be able to move it. It will overheat, overload the motor, and you cannot move it. Now, we come into this also that we work on this to lower our horsepower. These are standard motor horsepowers. They're always selected as the next higher horsepower motor. So you want, if you're over the line on one, you select the next line up. The red lines are not recommended. The horsepower increases with flow. That just makes sense. You move more water, you use more horsepower. However, the change resistance affects the flow more than the horsepower. So the resistance to flow will actually drop your horsepower. It shows it resists the flow of water. The horsepower will actually drop. Horsepower increases with flow, and it decreases with decrease in flow. Change resistance flex flow more than horsepower, and the higher resistance to flow means a lower flow and a lower horsepower. And we'll talk about that in a few more slides where you actually see what's going on. Again, at the 20 horsepower, or the 30 horsepower, sorry. 30 horsepower doesn't even meet the curve. Same thing with the 25 horsepower. In this case, we would not be able to operate on this family of curves, even though that curve says, the top one says that we can operate in there. It does not recommend it. Okay, so this is getting pretty narrow as far as our application goes. Again, all of these red lines, don't select it. Net positive suction head. This is what we're talking about, the cooling tower with not enough water coming in. It's the absolute pressure. Each one of these curves represents how much pressure you need coming in. PSIA, this is PSIA. Required at the suction inlet to prevent cavitation, boiling, and formation of bubbles in the water. I have more trouble with this on projects than anything else, which is strange because it's usually based on either a bad selection or somebody put a resistance in, or in most cases, a strainer is blocked where it's picked up garbage. So each one of these lines represents a different curve. In this case, 8 net positive suction head, 10, 15, 20. If you have a problem in the field, you have to have the minimum pressure pushing water into the pump, and that's where these lines come in. Otherwise, your pump will starve, and I have had more pumps show up if the pressure differential, the head, shows fine, but you're not getting the flow. So the pump can fool you to think, hey, I've got the right pressure, discharge, and suction pressure difference, but I don't have enough water, and this is why. Usually a strainer, somebody closed a valve on the inlet side, or somebody, in some cases, you've lost water and didn't make it up. So you actually got air trapped in the system somewhere that's fooling the system to thinking it's got water, but you really don't have enough water. Any net positive suction head above 15 psi would need suction above the pump in this case. You need, in other words, you would have to put that suction above the pump, that pressure to get a vertical head at coming in to actually improve it, because 15 psi is atmosphere. So if you were trying to pull water into a pump and you saw a negative 15 psi, that's as best as you're going to get, and you're not moving any water. All right, total head. Let's talk about how these interact. Total head and feet versus flow. Okay, this is the resistance. Select the operation of the best pump efficiency zone. So that blue line kind of tells us these are the straight line where we might get the best efficiency. Some engineers and designers select the pump based on the possible conditions. Again, the selection is made based on the design, but that's not necessarily what they're going to see in the field. So in some cases, they will select a pump to operate on one side or the other of this blue line. Okay, so that a change would either improve efficiency if I had a change in flow, or improve efficiency if I had a change in resistance. So it either move one way or the other from this blue line. If you want to go with the next set, you get a wider, which I guess you could call sweet spot, but you're losing 1% in efficiency, but it gives you a wider operating range. Okay. So if we pick at the very bottom of this thing, we can go all the way down to, what is that, 790 or 780 GPM. And at the very high end, we can go up to 1200, okay, and stay in this relative zone of good efficiency, below or above 80, or around 80%. But then I have to look at the resistance also. So the highest resistance I can have in this system is 83, somewhere in there, and the lowest resistance to get the best operation is 57 or so. 50, no, that's 53. So some designers will pick the operating point between these lines, okay? And that's where they think they can operate whatever conditions in the field. This also comes into play sometimes in our variable speeds, that we want to change the amount of flow we have. So if you really think of it this way, you can get up to 1200 or down to 8 or 780, as long as your resistance isn't above or below the red lines. Okay. That picks these curves, these three we can operate with in those zones. So it kind of narrows down where we can apply this pump. So if I said the design was 900 at 64 feet of head, I want to get into the green zone as best I can. The yellow zone's okay. Down in this horsepower at about 20 horsepower motor. Really, that's the biggest horsepower I can get. If I choose the 14-inch pump impeller at full speed, best efficiency is 81%. As head increases, resistance to flow, the flow will decrease. If I try to stay in that 80%, 81%, the dark green area is basically where I'm going to end up. Now, I could get into this orange area. Again, I'm operating in this zone, but my best selection is probably this 14-inch diameter, because it covers the entire range in head and feet and my entire range in flow. 65 feet of head will give you 850 GPM. So I'll pick the extreme, okay? That's the highest flow I can expect. My best efficiency falls right in here in that deep green zone. But then my flow goes down around 900. So that's really where I want to be. Then I'll pick it at that resistance. I hope my system resistance does not exceed this, because then it will restrict my flow. So I better be operating somewhere in this. See how the actual resistance narrowed me down. This is where I can operate with this pump and maintain my flow. Anything below that blue line as far as resistance goes. Max flow of 1050 GPM at 57 feet ahead, and a minimum flow of 760 at 69 feet ahead. So the higher resistance cuts down my flow. 20 horsepower, but the actual brake horsepower is going to be less. You'll see that later on. And 10 feet net potted suction head is needed for efficient operation. Less will starve the pump of water. So again, I have to make sure I see that. So I'm sure at some point we've all dealt with the affinity laws. So fundamentally, we take the pump curve and the pump information and we apply them to our affinity laws. And so this is where we start calculating out where we're going to operate. And remember that the flow varies directly proportional to the speed. So I've had a constant, now this is the interesting part, a constant impeller diameter. Why would I even think about a variable impeller diameter? I'll tell you in a moment. The speed can be variable. My specific gravity, basically the fluid that I'm pumping is constant. In this case, water is 1. If I want to correct for flow, the speed changes directly. The flow changes directly as the speed changes. Double the speed, double the flow. Half the speed, half the flow. Okay, simple. However, when we start talking about the head the pump can produce, it will increase if I change speed by the square. So, and it also decreases by the square. So we'll have some examples about this. Don't worry about this. Where we really get into the controversial part is the brake horsepower kW in variable speed. By the affinity laws, they say that if you change the speed, it will change the horsepower by the cube, okay, the cube of the change. And we'll see this example coming up. Horsepower varies as the cube of the change of speed. The change of speed changes the quantity of flow, which makes sense. It would change the horsepower required. More flow requires more horsepower, less flow requires less. The impeller diameter is a constant size. In the old days, and John may remember this, past energy management practice before variable speed drives was to throttle or restrict the pump discharge to meet the flow requirements. We would actually cut down the valve. We actually have balancing valves now to dial in the flow to the right head pressure or the resistance to flow to get the right water flow. However, the problem is that the speed maintained stayed the same. And if I had to cut that pump down a lot, it's going to really cut down. That again, you'll be riding the pump curve to the left and it starts resisting flow. So why would you do that? The alternative was to actually take the impeller out, take it to a machine shop and trim it down to a different size to better match the head versus flow versus horsepower requirements. And that was a permanent change. And you were pretty brave. And I've actually run into a few of these in old systems where they did this and they didn't tell anybody. So basically it throws the pump curve out the window. You have changed that impeller size and it has taken it away. If that was the case, you're kind of out there on your own. You'll have to come up with a different way of measuring flow. That's just the way it is. And I hope you don't run into that, but that was an energy management practice in the past. If you were constantly throttling down on the flow, your only alternative is to make a permanent change in the impeller. And that would be a change in the impeller diameter, which would make it variable. So change the impeller size, yeah, you'll change the flow and horsepower and everything. So let's talk again about total head and flow versus GPM. Zero flow, note the zero flow versus head intersection point. This is head, okay? Zero flow, right? And maximum pump head. That's zero flow at the maximum, if you shut the valve off on the discharge of the pump, this is what you ought to see. This is actually a test to test and see if you've got the right size pump, if you're dealing with that right size impeller. So in the 14-inch, I should see 83, 82 feet in head at zero flow. And that means I'm using the right curve. If it says something else when I do that, I've got something wrong. Something's wrong. Somebody's done something to change it. Then I got to check and see if I've got net positive suction head, issues like that. 0 GPM is typically the maximum head point on the impeller curve. 82 feet at 0 GPM is versus 900 GPM at 62 feet. Still requires horsepower, even though no true flow. So that operating point falls in between 10 horsepower and 15 horsepower. I'm still using energy at zero flow. Why is that? Well, the pump is a non-positive displacement device. In other words, it's going to pump right back into itself. If I've got nowhere for the water to go, it just pumps bypasses right back into the suction inside the case. If you run like this for a long time, it will heat up. You'll actually heat the water up, and I've run into that also, where you're basically, this term is called deadheading the pump. Long-term operation at this point causes cavitation. It heats the water up and eventually fails the pump seal. It will make the water so hot that it starts leaking at the shaft. It's more common in the field than you know, and this is something that we're going to talk about later on, about a real-world condition where we run into this a lot, and you'll be surprised in why. Okay, again, don't operate in that area. These areas are kind of the danger zones. You're above and below where it's recommended to operate. You will not see these points though on every curve. This curve just happens to have it. That's why I'm using it. Whether this pump actually exists in reality, I don't know. But back to our relationship. Flow direct is directly okay. Head increases, decreases with the square of the percentage, and the horsepower, again, change the flow, you will change the horsepower. Less flow, less horsepower. And to use this to plot what's known as a flow and head called the system curve. We will use these calculations to plot a system curve to give us an idea of where these pumps are going to operate against our system that we have in the field. So a system curve looks like this. It's plotted against a pump curve. Use the old the one I gave you an example, but this is a system curve with different points on the system operation, and each one of these A, B, C, flow at full load, and points represents where we're going to operate against the pump curve. But each one of them is a new point, but it's calculated out of those calculations. So if I plot my system curve over the pump curves, we calculate the flow at different speeds. This is where our variable speed comes in. We start looking at what the system looks like and what the pump operation looks like against that system curve. 90%, 80%, 70%. At some point, the flow, though, will be so low as to not be practical to overcome the resistance. We get below that low curve. It's just turning, but we're not real sure if we're moving a lot of water. Again, you're changing the speed, you're changing the horsepower, but you're changing the flow so much that we're not real sure how well it's going to operate at that very low end. So typically, I would say that below 40% is just not practical, especially on a very large system. And I'll give you a real world example here later on. Changes in horsepower as the flow changes. This is the energy benefit. This is how we get the benefits of variable speed, is that the horsepower drops significantly. But there is some discussion about exactly how to calculate that. Again, here's our operating point at the highest point. It's actually above the system curve, so this may be the large pump that we chose. If I go back the other way, though, where the horsepower crosses the system curve, I can actually get a little bit more water. That green line is where my design is. But as you can see, it intersects the system curve in a different point than the maximum on that curve, on the pump curve. So we're actually operating at a different head for that line at design. So I may be able to do a little better with a lower resistance and a little bit more flow that I can tolerate. Maxed out, though, on this curve, on that system curve, there are systems where they were overspeed the pump above 60 hertz. That's where you start looking at this, where you have to worry about your horsepower. Did you exceed the horsepower that you have installed when you go above that speed, that design point, to get more water? Or did you reduce the resistance of the system so much that you got above your capacity on your horsepower? This is where we really got to use this. You won't know this unless you go out there and measure it, or if you look at the pump curve and say, okay, what's my safe operating point? How high can I go with this thing without getting into trouble? And that's again, unless you do the measurements, this is your only other tool that you might be able to use to say, hey, I'm okay, or hey, I need to get a bigger motor. Other than touching the motor and burning your hand. I mean, that also is a good check. But we get the benefits of variable speed by reducing the flow and different points along the system curve all the way down. So in this case, we calculate the flows at different speeds compared to full speed. Now, remember also, here our design point in green. Remember also that every time you change the speed, you're not changing the size of your impeller. You're just redrawing this curve for that impeller every time you change the speed. There are actually software packages that can do this for you. I believe Bell & Gossett may have one, but you may have to pay for it. But you were able to, once you plot their curve for full speed, and then you punch in the change in speed, it recalculates the curve, gives you better numbers as far as your actual horsepower, the head and such that, your flow. And then you can have an idea of what your real numbers are versus calculating it out with using the affinity law. So in this case, the design point's in green. I'm doing it 510 GPM, 77 feet. On the 9.5 impeller, it needs a 15 horsepower motor. 65 feet of head on the system curve. This is the actual system curve. Needs less horsepower at the same flow. So the resistance restricted or cut back on your system flow or your system curve. But it needs less horsepower at the same flow just because of where it lands on the system curve. Okay, this is your actual system. Changes in horsepower as head changes, but flow stays the same. You see this in the pump curve. As the speed changes, the new pump curve is drawn to intersect the system curve. So you had the pump curve, now you plotted your system curve against that, and now you see a different point of performance at that design flow. Again, the pump is designed out of the factory, but once it's installed in the field, things change. And so that's where the system curve comes in. Again, here's an example using this different flows. We start off at design, okay? Design condition at 100%, 500 GPM at 1750 RPM. The total head is 70, and our brake horsepower required is 13.6. That's actually what we would measure. So we need a 15 horse motor, okay, to maintain the 13.6. If I go to 80%, reduce this flow to 80% by reducing the speed 80 to 80%, drops the head produced by 36%, but the horsepower, according to the calculations, drops by 51%. Or it goes almost half. Again, that cube law. If we go to 60% flow, the head produced by it is 64%. Again, that's the square. But the KW is down 78%. It's amazing. Typically, systems will operate between the 80 and 60% section. They rarely get up to 100%, unless you're at the very extremes of the design. And that's only, maybe 10% of the time, really. The design is there to maintain operation at 100% of your heat transfer. And the only times that you should see that is on those days that you have 100% load. That's rare. So we actually operate at 80 to 60%. Now, if we really get down to the low end, 40%, speed and flow down to 40%. The head produced, again, what it can accomplish, pump this amount of water against that resistance. We've dropped from 70 feet to 11.2. 11.2 is mighty low. And again, this is why I question operating below this point, because really, your system is still your system, and 11.2 feet isn't much. And the horsepower, the actual flow, is now down to less than 1 horsepower. Is this practical? I'm going to say no, because you did the calculations, and this is what we came up as a result. And I doubt, again, I said that even at zero flow, if you remember a previous slide, no flow at all, we still are somewhere between 10 and 15 horsepower because it's just pumping in itself. And that comes up on some systems. The horsepower does not track the same as calculated. Don't forget the pump efficiency also changes with flow, speed, and head, but we did not calculate that. That's another presentation. We could spend a lot of time just on that. A new performance curve is drawn every time the speed changes. So if you look at this chart, as we go down the system curve from 100% down to 80%, 60%, 40%, look at 40%. It's down there at 11 feet at 200 GPM. I don't know. I don't know if you're going to operate like that at all. You really got to question your operation if you're running down that low for very long periods of time. You're saving a lot of money, but are you actually doing any work? I would think that you would be wasting more money operating way down there at 40% a lot of the time. But that requires a judgment call to change how you're actually operating. Okay, and so this curve, this actually plots all the possibilities, variable speed, flow. This is what the actual operation of that pump looks like. All the possible permutations for that pump to operate across this entire range of flows and head. Again, they kind of stop at 20 feet in this case, but they'll max you out above 600-700 if you really get to the extreme where you reduce the resistance to flow and speed it up. But high and low flow, high and low speeds, changes in resistance to flow, that's head. Pump efficiency is affected in these extremes. Certainly, if you remember your pump curves, they don't improve when you move more water or remove less water. They are in a sweet spot. They have an ideal condition to operate in, and that's somewhere in the middle. So if you went wide open on this thing, you're going to lose efficiency in the pump. You'll move a lot more water. You'll use a lot more energy, but your pump efficiency will fall off. Stay in the middle for your best performance. So real world conditions. This is a system that I work on. Very successful, but when I got out there, you may have seen this before. You've got 2 chillers, 2 pumps. Pumps are common together. But you select how many chillers you're going to operate on based on the cooling load. And the question I always ask when I look at a system is, what is the DP setting and why is it there? In this case, they had it set up so high that it was above the zero flow point on the pump curve. Now, if I didn't have the pump curve, I wouldn't know that because they had set this thing above the zero flow point on that curve. The pump would never reach that because basically you're asking the pump to run at a dead head condition. The only way, even if I shut the valve off, I would never see that pressure differential at the pump. So they'd set it up so high because more is better, right? What they had thought was if I keep increasing the pressure setting, it speeds the pump up and I need more water, right? Right. Well, that's what happened. The pump sped up, but it wasn't the right approach. It defeated the benefit of variable speed. The chillers would just sit there and trying to deal with this higher flow, and it just wasn't very efficient. So what we did, we started using a more reasonable approach to setting that pressure differential. Started getting some actual change in speeds on the flow. It improved the performance of the chillers to where now we're operating right on the line to where we now take full advantage of both variable speed on the pump and the variable loading on the chillers. As the load changes, the chillers change their loading, and they operate in a better kW per ton point now that it's actually working right.
Chris, can you just for some of the folks, can you explain we'll go back to where you were, the differential pressure sensor and how that is used? And you just mentioned the DP, and some folks don't know what it is or why it's used. And
so a typical control strategy is to vary the speed of the pumps based on the pressure differential out in the system. So that DP will show like 2/3 of the way down the system on a branch. So you got some idea of how much pressure you've got, and that's where our 40% line comes into play, is that you want a pressure differential out there on the system, not at the pump. So you'll never see that pressure differential at the pump. Out in the system, it's going to be lower than what you'll see at the pump. But that's a way of telling you, hey, am I still moving water out here? If I get a pressure differential on the system, I know I'm moving water, and it's working against some resistance out there in the system. But if my pressure differential increases, that means the system has changed, and I can actually back the pump down to match that change, to get a better match on my flow required versus what I'm able to pump out of the pump. And so some strategies will say, okay, change the setting on the pressure differential. Some of them will set it a fixed setting and just operate on that, where the pump speed will change as long as I maintain a constant. That's not good, because you're basically saying that the resistance to flow is going to stay the same, and you change the speed of the pump. That means you're keeping the horizontal line constant all the time and just riding that pump curve back on the flow. Well, you can save a little bit, but not a lot. So what we typically end up doing is we change the pump speed based on a system change out there and reset that pressure differential setting to change as the system changes. Probably the simplest would be to look at a chilled water valve, in this case chilled water, to maintain it wide open. If it starts closing, I slow down the pumps, and then it'll open back up. And then I'll speed them back up. But I'll constantly be changing the pump speeds in response to what's going on out there in the system, rather than actually measuring and changing my differential pressure, hoping that I'm doing the right job. Now, sometimes a tab firm will tell you what pressure you need to operate on it, but not always. But so that's something you got to watch for.
If you've got like 10 air handlers being supported by this system, and you're going to look at see if there's any one valve that is fully open. Is that what you're saying?
Right. Speed up the pump if it's wide open, and if it gets satisfied, and it starts to close, and you can slow down.
So, but you're looking at all the valves, and you're looking to see, okay, I'm going to pump until one of them is fully open.
Right. But then if you use your pump curve, you're going to see, where is my pressure differential going to exceed my flow? And so that's where the zero flow line comes into play. Is these are the pressure differentials on the pumps, those curves that you cannot set your settings above. Do not set your settings above that. In fact, do not set your settings above where those solid lines and the zones, that limit where you need to operate. Otherwise, you're just spinning. You're not going to pump water. You're just wasting energy. It'll run at 100%, but it'll never move any water. It's like deadheading the pump. Okay. Another example, we got a primary loop and a secondary loop, pumps on each side. In this case, the primary loop is a constant speed, but my secondary loop is variable flow. And so in this case, the design flow is only 200 GPM for the cooling load. So the chillers are redundant. The pumps are on the primary loop are 200 each. But I also have a minimum flow that required on the chiller of 150. So the question came up, why don't we put drives on those pumps on the primary side? Well, I've only got 50 GPM to work with. If I go below 50, my chiller shuts down. I can't do that. So they put this decoupler in to where I can run 200 GPM constantly on that loop. Okay. I'll pump that water into the secondary loop, where I run one of the variable speed pumps up to 200 according to my load. And it comes back at 200 GPM. If I'm at full load, all 200 GPM come back to the chiller. Perfect. Works great. However, if I've got 40-degree water coming out and I got 50-degree water coming back, this is where my ideal condition was going to be. But somebody changed the settings on the pressure out there in the system to run the second pump. So now I've got 400 GPM pumping through the building, and I've got 400 GPM coming back on the plant, but I've only got 200 pumping through the primary. Where's that other 200 go? The other 200 50-degree water gets pumped back into the loop of my 40-degree water. 50-degree water at 200, 40-degree water at 200 GPM, comes up with like a 45-degree temperature water going into my building. So I'm trying to pump 40-degree water into the building, but I'm getting 45. And then I get, if I maintain the 10 degrees across the building, I get 55 coming back. Eventually, that 55 degrees works its way into the central plant, which makes the second chiller come on, which starts the second pump. We now have 400 GPM in the plant, and it's going through all the way through the system, way off the chart. I'm operating full bore for no reason at all, and it's ridiculous. Okay. Now, this is probably the biggest nightmare. This is actually a system, 3 separate sections: central plant, secondary to transfer the central plants in its building by itself. The pumps then transfer the chill water out of the plant to the building. Okay. But I've got in the central plant 4 duplicate chillers, a duplicate variable speed pump, dedicated pumps, but the pumps are all different sizes and flows. Somebody got the wild idea to get the cheapest pump where they could find. They come up with a pump that actually pumps higher than what the design required and put it in. And so now I've got this headache where if I'm running this chiller, I've got to run this flow, and nobody knows how to do this. So what we ended up doing is to print out a chart using our affinity laws and the pump curves in order to operate on. And in this case, the plant decides where it needs to operate. Let's say it's 65%. It makes a determination, okay, I need 3 pumps, but each one of the pumps, according to which pump I'm running, you set at different speeds, okay, in order to maintain the right flow through the chillers. But I need my pump curves to tell me which one of these is going to operate. So I've got one running at 52%. I've got another one running at 65%, and I've got a third pump running at 57%. So those would go in to maintain the right flow through the plant, okay? Then I have to deal with the secondary loop. These pumps just run to transfer out of the plant into the building. So again, I have to figure out, I'm operating 65%. That's where the pumps on the primary, on the chillers will operate. Then I have to decide how many pumps on the secondary I need, and those end up to be, I need to run 2 pumps at 65% in order to come close to match that flow. What I'm trying to do is to match the flow out of the plant to the flow to the building so that I'm not running water back through that decoupler back into the plant. And in this case, the 2 pumps running on the secondary at 100% did not equal 2 times the flow. They actually were fighting each other. And so when the second pump come on, the resistance to flow increased. Better performance was 80 to 50% or below. Now, again, when I said at 40%, that's when the determination to shut it off would come in. But this chart is what we're trying to automate into this plant. Now, the real unknown I've got at this point is the building. Okay, so it's got multiple pumps, all different sizes. Some of them are variable, some of them are constant. I've got to really watch what's going on. So in order to defeat this or to manage it, we watch the water temperature coming back out of the building. So we operate the central plant based on a temperature difference that comes out of the building. As long as I match my flow out of the plant with the flow on the secondary into the building, I can maintain a temperature difference across my plant without having to fully automate my building. That's the next step. But it's mainly derived to maintain a constant differential temperature. So I hope you can readily see, or at least find something to use in the pump curve to help you diagnose issues with system performance. The opportunities in energy management optimization are right there with your horsepower and flow. The pumps connect the energy system, source and sink. Efficient operation is always key, especially in that last one where I've got All those pumps trying to transfer water from the plant to the building, and it's a vital to in selection and troubleshooting of the systems. So
Questions?
Yep.
Let's go. Thanks, Chris. That was good.
Yeah.
It's a lot more complicated than I like. No, not the presentation was. Reality is. I always like things where it's just black and white. It's on or it's off. That's it. And it's not that way. Okay, here's question number one. How do we practically measure for these different situations in the field in an audit situation with or without changing the system?
So, good question. Get your pump curve, get you a hydronic manometer, or some way of accurately measuring the pressure across that pump. You can actually plug in, and I've got a very good one. You can plug in that pump curve where it operates at full speed, and then it will actually calculate or try to meet whatever flow you're doing according to the change in the head at the pump. In the case of that last example, we're actually putting flow metering on each chiller to measure the flow and drive those drives to maintain flow automatically. Right now, the operator has to punch in those speeds. But that would be the next step, is to actually put in accurate flow metering to get an accurate, but you're always constantly checking to make sure that what you're reading in the system is what's actually going on. So the first step, pump curve, hydronic manometer.
Okay, here's a question. I think there's some research out there that shows that exponent for, what is it? Speed of the pump versus kilowatts is, it's not a 3, the exponent, but like 2.2 or 2.1. Exactly.
So there are programs out there that will calculate these out. And if you're on a drive, you can actually read the horsepower directly. And you'll do the calculations and you'll read the drive and it's like, what's wrong here? Which one do I believe? I believe the drive. That's the one that's going to tell me where I'm operating at.
Yeah. Okay, so here's one. I would think that the brake horsepower under the BFD operation is roughly linear with flow when a DP sensor is used to maintain a constant system pressure differential, not cubic. Yes or no? Is it, or is it just complicated?
That's a derivative of what you just said, the previous question. Yeah, when you're maintaining a constant pressure differential, you're drawing your line straight across on your pump curve and then just changing the flow. But remember, we draw a new pump curve every time we change speeds. So, if you're trying to maintain a constant pressure differential, you're going to move the flow to the left on the pump curve and then redraw the line, but you're maintaining a high resistance when you really shouldn't need to. So if you're maintaining a constant pressure differential, you're basically telling the pump you're going to operate basically right in that pump curve by changing the speed. But you're going to limit the amount of opportunity you've got, because eventually you'll get down to the point that your speed drops to maintain that pressure differential. You cannot maintain it. You'll speed back up to maintain a pressure differential, not flow. Okay, that's why we're looking at flow. The resistance changes your flow. You're not changing the resistance though when you keep a constant pressure differential. Okay. I'd rather change the ability. I don't want to change the resistance to flow, because then I can really reduce my horsepower and change my flow.
Okay, next question. Is the differential pressure set when balancing the system by the commissioning folks?
It's usually done by the tab firm. The tab firm will tell you that this, so tab, a little insight, I'm a tab guy, sets the design conditions, so 100%. Okay, they don't really test the 50, 40, 30%. So they will set the 100% flow on all your equipment and where that system should operate if it was running at 100%. They measure then the pressure differential at that point and say, okay, operating at 100%, here's the pressure differential, adios, I'm out of here. Where it gets into the energy management side is people like me start operating between 100% and 40% and say, okay, I need to do better. I know where the top end is. Now I need to know where I can go from here to reduce energy management. Commissioning helps in the energy management, but it's not based on energy management. Retro commissioning is, but the commissioning of a new system doesn't necessarily focus on energy management. They're not focusing on operation. I want to make sure that this thing operates across the spectrum. I don't care what the energy is, or I don't care to optimize for energy management. So retro commissioning, people like us, that's where we step in and say, okay, we can do better.
Right.
But that's set at tab. That's set at the original maxed out point.
Okay, here's another one. Using variable speed and affinity laws, I know you can save energy by running cooling tower fans at the same speed to share the load. Does it make sense to do load sharing with pumps?
That's exactly the example in the third example. I could run 2 chillers at a higher capacity or higher flow, but maybe not necessarily more efficiently. So I choose to run 3 chillers at that 65% load because I can't run, this is where the system restriction comes in. I could not run those 2 pumps efficiently. 1 pump could handle the load, but 2 is better.
Okay, so I want to restate this maybe in simplified language that my brain understands. You're saying that it is more efficient to run 3 pumps at a lower load than 2 pumps at a higher load.
Yep.
That's what you're saying.
That's what I'm saying.
The chiller person would say it's more efficient to run 2 chillers at a higher load than 3 chillers at a lower load.
Well, there you get into, and then probably another idea for a webinar, is chiller efficiencies at part load. Then you start talking about how your kW per ton falls out. In this case, these chillers had 2 compressors on them at variable speed on both of them. So if I can get close to 50%, I go to 1 compressor running high versus 2 compressors running very low. But you need to look at your chiller efficiencies at part load to find their sweet spot. Again, back in the old days, we thought 100% was best. No, we found out that 60, 80% is better.
All right, here's the question that I asked you earlier that I didn't ask, someone else asked it in different language. My colleague insists that operating 2 pumps in parallel at reduced speed, let's assume with a VFD, is more efficient than 1 at full speed.
Again,
I disagree. I disagree. As the required pumping energy is determined by the system curve, not the pump curve. Lower speeds affect the efficiency point as well. Opinions?
Correct. It affects the efficiency. Again, like I said, if you run really low with 2 pumps, you're not moving the water like you should.
Well, there's
so
that. That's really low. That's an extreme.
Yeah, but not. Again, I said 40%. I don't want to go below 40%.
Right.
But if you look at your pump curve, you can see that that you're getting down to the point that you're not pushing against resistance. You're not pushing the water like you should in volumes you need to. So it's a trade-off. Running those 2 pumps or 1 pump at full speed did not give me the amount of water I needed by running 2 pumps at a lower speed. Running those 2 pumps at a lower speed gave me the flow I needed against the resistance of the system. And the actual energy used could be a trade-off, but I'm thinking that a lower speed, the efficiency improves. The efficiency basically rides that system curve down. So you're running, if you system curve falls into the most efficient operation of the pump, I would expect that efficiency to track down that line of the system curve. Okay.
Here's a related question. This is mine in different language. You have 100 horsepower pump running full. No, I'm sorry, at 50%. It's running at 50% on a VFD. Or you could replace that whole system and put in a 50 horsepower
running at 100%.
Pump running at 100%. Which one is going to use less energy?
So it's according to what energy, again, at the 50% point of the 1 pump, is it running at the same energy level as the 100% pump?
At 50%.
At 50%, yeah. So again, if you could compare the 2 curves, looking at one of them running at 100%, another one running at the 50%, if they're practically, if they are practically the same, that's a possibility. Now, I'm going to say that one of them probably is a little better than the other, that the two pumps running lower is better than the one pump running at full speed, because you better be in the sweet spot on your efficiency at full speed. That's again where the efficiency comes in. Does it stay efficient at 100% and stay efficient at the two running at 50%?
Okay, so a similar question. So there's this equation for pump kilowatts, or let's say motor kilowatts. 1.0, not one, no, it's 0.7746 times horsepower times load factor divided by efficiency times the VFD percentage to the 2.2 power, or 3.
The square root of the phase, right?
Yeah, I mean, it'd be the cube root, but I'm going to derate it to 2.2.
Right.
Okay, so that equation. Now, my question here is, if you're on a VFD and the VFD, goes down from 100 to 75 to 50, does the load factor change in that equation? The same. Not sure is an okay answer.
I'm not sure, because I'd have to really look at that. My experience has been in real world, okay, and I'd like to see that in practice, and maybe I can do some experiments on that.
Yeah, let me get with you offline and let's talk about that.
I'd like to see that along with the parallel operation. I've seen better operation with parallel pumps at lower speeds than the single pump at high speed.
Okay. Here's another one. What happens when you use a manometer to match a pump curve, but they may have changed the impeller and it doesn't match anything?
Yeah,
that's based on the nameplate impeller best you can, or are you just stuck?
You're kind of stuck unless you are good enough to draw a shutoff head to full flow curve for the new impeller. I'm sure there are some bright minds out there that can calculate what the flow, or redraw a pump curve based on the new impeller, or the impeller that doesn't match any curve. I am not one of them. Like I say, I've seen that in the field a couple of times based on the old way of doing it, that you could run at full speed with all the valves open, but they trimmed the impeller and didn't tell anybody. So nothing matches anything you've got. You end up going the flow meter route. You end up putting a flow meter somewhere in there and coming up with your own pump curve based on speed and flow. So you start calculating, or you start tracking your speed and flow based on that new pump, and you're basically making a system curve based on that. You operate on that.
How do you go about finding pump curve data, especially for existing buildings with limited information?
Well, that's a good question, because that third example had you got a nameplate. It's supposed to have a nameplate on the pump that gives you fundamental flow at feet. Okay, that's fundamental. Sometimes they'll put the pump impeller size on there, but the manufacturer keeps track of just about every job they sell, and you would end up having to go back to the manufacturer if you can get a good number off of that. I actually had one that was really bad. Sent him a picture of it, and he was able to find it. I was amazed. But that's your only thing, is going back to the manufacturer, unless, like Bell and Gossett, I think, was the one that actually had a program out there that you would have to purchase. It had all their pump curves in it. You punch in their numbers and it comes up.
Well, how many pump curves are there out there? I mean, are there like
millions,
thousands of them?
Millions.
So there isn't like a catalog online, like, you can type in a package unit, model number, and you can often get some information, but it's a lot harder with pumps, you're saying?
It is. You can try that online, and the internet is your friend. But again, your question about speed, that's usually a trip up.
Yes.
You get a pump curve, but it's the wrong speed. Right. Or you get, it's just not going to match, or it's so old that you've got to ask somebody and they will send it. And I've had really good success with manufacturers. They are willing to, actually the vendor probably is your better bet, is the guy who actually sold the pump, who reps that line. And they may even have the file on the project that they sold. As a tab guy, I look to submittal data that the original project submitted this pump. They have the curves in there,
That's right.
what they're supposed to do. So that it helps you if the people have the documentation, the building, if they have the documentation still handy. That's first question I ask is, do you have that?
Yeah, that's good. If we have the pump curve and we know the differential pressure and we know our impeller size, then can we get the GPM off the pump curve?
Yeah, if you read your pressure differential, it's the intersection of those two lines. You find the curve, you find the pressure differential, where it hits that curve, draw the line down vertically, and that's your flow.
All right. Chris, thanks so much. And I'll see you in a month or two. I guess it's November. No, October? October. Yeah, in a month. Okay. Talk to you soon.
Yep.
Bye, everyone.
Thanks, everybody.